All right. Very, very, very big day today. Exciting one. Okay, so natural base E. What is E? Yep, natural base E. What is E? All right, most of us are going to say, well, it's a letter. Yep, not anymore, people. E is a number. Now, tell me what we know about pi. What? It's 3.14? Yeah, it's an irrational number. Pi is a number that cannot be written as a fraction. Guess what E is? Another irrational number. Another number that cannot be written as a fraction. And our number E is approximately equal to 2.7182818 and a whole bunch of crud after that. Forever and ever and ever and ever. Now, E comes from this expression. This equation, f of x is equal to 1 plus 1 over x all to the x power. All right, we're going to try a little experiment here. Want to make sure that we are... Grab calculator very quickly. 1 plus 1 over x to the x power. I want you to plug in the number that I tell you. So, 10, 20, 20, 30, 50, 70, 90, 110, 150, 175, 200, 250, 300, 400, 500, 600, 700, 1,000, 2,000, 3,000, 4,000, 10,000. All right, plug in your number. What? What? I don't know. What number do you plug in? Okay. All right. Hopefully. All right. Let's take a sample here. All right. We plug in 10, we get about 2.59-ish. Fair enough? What number do we have? What? No, what? 50. Plug in 50. Plug in 50, we get about 2.69. Plug in 150. Plug in 150, we get about 2.709. All right, we plug in 175. 175 gives us about 2.710555. All right. What do we plug in? All right, we plug in 600. Took a big jump here. We plug in 600, we get about 2.7160. 1,000, right? That's one of my favorite numbers. All right. We plug in 1,000. We get about 2.7169239. What do we got? Plug in 3,000. Plug in 3,000, we get about 2.717828. Anybody notice something that's happening? We are getting closer and closer and closer to that number. We plug in 10,000. We get 2.718145927. The bigger my number, the closer I get to E in that equation. The bigger the number I plug in, the closer I get to that number. So in other words, what we're saying here is as x approaches infinity, f of x approaches, beautiful, As x approaches infinity, f of x approaches e. The bigger the number I plug in here, the closer I get to e. If I plugged in 1,000,000, I'm hoping it'd be pretty close to e. All right, now, what we need to remember is e, like pi, still works like any other variable. So when we are beginning to simplify the expression on the quizzes and tests this chapter, you will have sections with no calculator. This is one example of something that I would ask you to be able to do without a calculator. Simplify the expression. So if I have e to the 9th times e to the 6th, Lena, what are you thinking that is? Beautiful. Power times the power. I add those exponents. E to the 15th. All right. What are we going to get for b? Ben K, what do I do for b? Okay. So what do we end up with then? 60 Okay, 60. Power divided by a power I subtract. So 8 take away 3 is e to the 5th over 12. What about 60 twelfths? You bet. 12 goes into 60, 5 times e to the 5th. Power divided by a power, I know that I'm going to be subtracting my exponents, not changing any rules. Hunter, when you look at C, are you excited? Yeah, what are we going to do in C? All right, we're going to do negative 10 to the 3rd. Okay, so I'm going to take that in 2 steps. E to the negative 5x and then to the 3rd, right? Now, Hunter, what do I do in this situation? You bet. A power to another power, I'm going to multiply those exponents. Fantastic. So negative 5x times 3 is going to be e to the negative 15x. And what is negative 10 cubed, folks? Negative 1,000. All right, am I done with that one? Why not? You cannot have a negative exponent. Cannot have a negative exponent. So, Brianna, what am I going to do to get rid of that negative exponent? All right. Beautiful. All right, e to the negative 15x, I'm going to move it to the denominator, become e to the positive 15x. My negative 1,000 stays in the numerator. It does not have a negative exponent. Perfect. Questions, concerns? All right, now, here's the deal. Sometimes we are going to need to use our calculator to be able to evaluate an expression. Typically, and yes, I know on graphers there's an E button also, but typically the E that we are looking for is second ln. Second ln. And E is oftentimes used, or most of the time used, as e to a power. So if I just want the number E, if I do second ln, if I just hit that second ln and try to hit enter, my calculator is going to give me an error. If I just want the number E, I need to take that E and raise it to what power? E to the 1st. All right, go ahead, quickly do that. What should I get? What should I get? Yeah, and what is that number? About 2.71828, blah, 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 blah. Yes. If you're having troubles with the calculator, let me know and I'll come around and help. Exponent in? Yeah, I would have thought so too. Second LM. So that shift that one, and then the imported one. All right. have to go in the second pie, which is your log menu, and there's a lot of things in the next couple days that are gonna be in here. Arrow over, e to the power, and then put 1. Okay? Anybody else? Issues with their machines? Everybody's are a little different. Okay. All right. Then, if I want to know e to the 6th, I want a decimal approximation. Let's go ahead and very quickly do that to make sure we know what we're doing on our calculator. What do we get for e to the 6th? What do we get? All right. About 403.4288 if I take it out to 4 decimal places. Does that seem reasonable? All right. How about B? E to the negative 2800ths. How about e to the negative 2800ths? Marcus, you got that? Did everybody get 0.7558? Okay, now here's the deal. I want you to understand something very important here. If I take e to a positive number, what type of number do I get? Pretty big one, right? Pretty big one, 400 and something. If I took e to this negative number, what kind of value did I get? Small, a decimal, right? Okay, keep that in mind. Keep that in mind. I want to point that out to you right now because I think that will help us in a few minutes. All right, now, natural base functions. If I want to be graphing these, thinking about graphing these. If I'm thinking about graphing them, in a function like this, my parent function is going to be y is equal to a, e to the rx power. It's called a natural base exponential function. Notice x is still in the exponents. Now, we're going to look at y equals e to the x. I want you to think about this parent function. Y is equal to a times e to the rx power. Y is equal to a times e to the rx power. Now, what number do I have for a? What number do I have for a? 1. What number do I have for the r value? The r is the coefficient on the front of the x in that exponent. A 1. Okay, now let's think about y is equal to e to the x. Really a basic graph as far as exponential e graphs are concerned. Okay, if I'm here at x of 0, where will I be on this graph if my x is 0? Okay, think about this. If I take e to the 0, what am I going to get? Anything to the 0 is 1. Okay, anything to the 0 is 1, so I am up at 1. All right, now we know it's going to be exponential growth. We know it's going to go up and to the right and come down and to the left. And just a comment, if it's exponential growth, what else do we know? It gets closer and closer to that x-axis, but never touches it because the x-axis is what, Heather? The asymptote. All right, so it's going to be that dashed line that my graph approaches but never touches. All right, now notice that it crosses the y-axis at my a value just like yesterday. That didn't change. Okay, so my y-intercept in this case is going to be at 0, 1. My asymptote is at y equal to 0. What about my domain? Marissa, what about my domain of this graph? All real numbers, absolutely. And what about my range? You bet. My graph is above that x-axis. It's above that line at 0, so y is greater than 0. Now, remember, I want to just make sure that we make a note of this so that we remember my y-intercept is always at 0a. So in this case, that is how we got 0, 1. My y-intercept is always at 0a. That is not going to be changing. Okay, now over here. Going to take a look at our exponential decay graph. We're going to take a look at y is equal to e to the negative x. And I want to just show you a little bit of work off to the side here to get started. Okay? They're telling me it's exponential decay. I want you guys to understand why that happens. Okay? Realize we know that the equation they're giving me is y is equal to e to the negative x power. Y is equal to e to the negative x power. Now, I want you to think for a moment. A power to another power, what do I do with my exponents? Multiply, right? Okay, so e to the negative x. Is it legal for me to say, well, that's y is equal to e to the negative 1 and then to the x? I didn't do anything illegal, right? E to the negative 1 into the x, this is negative 1x. A power to a power, if I multiply that, I get back to negative x. Okay, now I got a question for you. What is e to the negative 1? Well, it's 1 over e. All right, do yourself a favor very quickly. What is 1 divided by e? Very quickly, we're going to get a cruddy decimal, I realize that, but what is 1 divided by e approximately? About 0.3678 to the x power. Now, what does that tell me? What does that tell me? What is, okay, wait a minute. Let's look at my parent function here. Y is equal to a from yesterday times b to the x, right? Yesterday we were looking at y is equal to a times b to the x. In this case, what's my a? And what's my b? About 0.3678. If my b is about 0.3678, what does that tell me about this situation? It's exponential decay. When my b value is between 0 and 1, we know it's going to be exponential decay. So, anytime we have e to a negative power, I know my graph is going to be exponential decay because e to a negative power is going to put that between 0 and 1. So, if I take a look here with my parent function, y is equal to a times e to the rx. We write it differently than a times b to the x. Y is equal to a times e to the rx. What number do I have for a, Kennedy?
1.
All right, my a value is 1. And what's my r value?
1 over e.
Careful. My r is the coefficient on the front of x in my exponent. It's negative 1. Good. And if my r value is negative, if the exponent is negative, we know it has to be exponential decay. Has to be exponential decay. Okay, so let's go ahead and try to make this graph. All right, where am I at 0? At 0, I'm up at 1. And then I know that it's going to be exponential decay. I know it's going to look like this. It's going to come down and to the right, getting closer and closer and closer to that x-axis, but never touching it. So that x-axis is my horizontal asymptote at y equals 0. All right, what's my y-intercept, Brooklyn? Good. 0, 1, or just 1. My asymptote is y equals 0. What is my domain, Aaron?
All reals.
Beautiful, all reals. And what about my range?
Y is greater than 0.
Y is greater than 0. I'm above the x-axis, so y is greater than 0. Does anybody have any questions or issues with that? Yes?
X is positive, it's exponential growth.
If my exponent is positive, it's going to be exponential growth. If my exponent, the r value is negative, it's going to be exponential decay. That is exactly right. We okay? All right, let's continue on. All right, going to graph a couple of these. I want to make sure that everybody knows exactly what to do when you are graphing. So we have y is equal to 4e to the 0.5x. The first thing I want you to do is, okay, there's an e in there. I'm going to write down my parent function. Y is equal to a times e to the rx. Looks a little different than y equals a times b to the x. But remember that that b is just the e to the r power. All right, so what is my value for a, Ben M? 4, and what is my r value? 0.5, beautiful. Is this exponential growth or decay, Jenny? What? It is exponential growth, absolutely, because my r value is positive. All right, give me 1 point on this graph, Ashlyn.
0, 4.
Beautiful. I know it's got to cross the y-axis at A, so I'm up at 0, 4. Now, here's the deal. We know that my graph is going to go like this, but to make sure that we are as accurate as possible, I want you to find at least 2 other points on this graph, okay? I want you to find at least 2 other points on this graph, and it's not as easy as when we have a times b to the x. Okay, so I probably would find -1 and +1. All right, get out your calculators. They're going to be decimals. They're going to be messy. So if I plug in -1, a half times -1 is -1/2. So I'm taking e to the -1/2 power, and then I'm multiplying it by 4. Jacob, do you have that? What do we get for y when the x is -1? 2.426-ish. What do we get when we plug in +1? Becky, do you have the value when we plug in +1? 6.59. Do we agree with those two values? Does everybody agree? Anybody having difficulties with their machines? Let me know. All right, so -1, we're up at 2.4-ish. You got to estimate. 1, we're up at 6.5. And notice my graph goes up and to the right and down and to the left. But what, Dennis? It's going to stay above that x-axis because that x-axis is my asymptote. Asymptote at y equal to 0. All right, what is my y-intercept, Chelsea? 0, 4. All right, how about the domain? Maddie, what about the domain? And what about the range? Beautiful. Above the x-axis, so it's y is greater than 0. Fantastic. Any questions so far? All right, let's take a look at B. What is going on now here? What are we adding on to the situation in B? All right, we got an h and a k, and what do those h and k values do to this graph? They shift it left and right and up and down. Now, the first thing I want you to do is find the parent function. Does somebody have a thought on what the parent function is for this graph? I want you, and I was very clear the last couple of days, I want you to graph the parent function and then show the relationship with the shifting left and right and the shifting, the sliding, the translating up and down. Anybody got a thought on what the parent function is? Kennedy?
Y equals e to the -1/2x.
Beautiful. Our parent function is always everything up through the x. Love it. Y is equal to -e to the -1/2x. So y is equal to a times e to the rx. All right, what is my a value? Lena, what's my a? And what's my e? Excuse me, my r? You should have just said 2.71828. All right, my r value is -1/2. Now, what do we know about this graph? Aaron? It's decay. My r, and I even wrote it as e. My r value is negative, so it's going to be exponential decay. All right, looking at this graph. Give me a point on this graph, Brooklyn.
0,
0, 1. All right, gonna graph 0, 1. All right, need to find a couple other points. Build my XY table, plug in -1 and +1. Let's find out what the Y values are for that parent function. All right, what do we get for -1? Jenny? Okay, all right, let me come there and help you.
No, the parent function, So -1.5 and -1 to be positive 1.5. So I'm just gonna take E again, second LN, E to 1.5.
Always put it, we're plugging them in the parent function because it's a whole lot easier to find our values. And it shows the relationship that these things have. All right, so what do I get when I plug in -1, Marcus? About 4.48. And what do I get when I plug in, substitute in +1, Marissa? About 2.223, beautiful. So -1, I'm up at about 4.5. And at 1, I'm up at about 2/10. Got to estimate as best I can. Exponential decay, I know that graph is coming down and to the right. I know it's getting closer and closer to that x-axis, but never touching it because that x-axis is the horizontal asymptote. All right, so there's my parent function. Tara, what happens to that parent function? Beautiful. That x plus 2 means that I move it left 2. Those -4 at the end, my k value of -4, means that I move it down 4. All right, first thing I like to move is my asymptote. If I move that asymptote, where is it going to be moved to? Chelsea, where will my asymptote move to if it's going left 2 and down 4? Beautiful. My x-axis, the y equals 0, is going to shift left 2, doesn't do anything, but down 4 puts it at y equals -4. All right, and then I'm going to take each point, shift them left 2, down 4. You got to estimate as best you can. Left 2, down 4. Left 2, down 4. Left 2, down 4. All right, what is the domain of this situation, Jacob? All reals. What about my range? Beautiful. I'm above that line at -4. Now, want to add one more thing because I promise you I'm going to be asking you this in every situation. What is the y-intercept? How do you get it? All right, my y-intercept, we always know that the x is 0, and I have to plug that into my complete function. So y is equal to e to the -1.5 times my x of 0 plus 2, and then subtract 4. All right, so 0 and 2 is 2. Negative 1.5 times 2 is negative 3, so I'm going to take e to the negative third power, and then I'm going to subtract 4, which should give me about negative 3.59. So approximately negative 3.59. Does anybody have an issue finding that? I'm going to always be asking you for the y-intercept. Other questions?
So if you, on like a tester, physically draw the graph and it touches the asymptote, you keep running.
It never touches that asymptote. It gets closer and closer and closer to that asymptote, but it never touches it. Okay? Always got to keep that in mind. I'm not going to be too picky, like my arrow here touches this a little bit, but when people draw them and then they draw it underneath, I'm going to get very unhappy with that. It's a wall. It gets as close to that wall as it can, but it never goes on the other side of it. It never goes into it. Okay? All right. Now, example number 4 is a story problem. Story problems are going to be messy. As we have in the past few days, what are we going to use to look at those graphs? Absolutely, graphing calculator. Now, this problem is discussing annual sales of a certain product can be modeled by this function, where S is the number of units sold and T is the number of years since the product went on the market. Now, just a comment. We look at that equation. What do we know about this situation already? It's decay. So what is happening to the number of units sold as the number of years goes up? Goes down. They're selling fewer and fewer and fewer products. We know that before we even begin with the graph. I'm not going to go through the graph because I feel like we're doing a fantastic job already of putting these in our graph or adjusting the windows. The situation is the same as we've been doing the past few days. Okay. Then, one example of where our number E is used is continuously compounding interest. Now, we have talked about banks finding the interest with our equation of A is equal to P times the quantity of 1 plus R over N to the NT power. Where am I going to make more interest? My bank gives me the option. Should they compound the interest every year or every month? Where am I going to make more interest? Every month. Okay, they give me a choice between every month or every day. Every day. So ultimately what we're saying is this. The more times that we compound it, the more interest that we make. I'd much rather have it do them every month than every year. I'd much rather have them do it every day than every month. So what happens if we could do it every day of every year, of every minute, of every second, constantly, continuously? Somebody sits at a desk and they find our interest, they put it in the account. They find the interest, they put it in the account. That's what they do all day long. Crunch numbers and have fun with math all day long. Continuously. They're just working away, putting that money in the account, and then they do it again and they put it in, and they do it again and they put it in. Is that going to be better for me? Yes. Yes. That's the best thing that could ever happen. You'll never find a bank that's going to do it. But we don't need a little person or a big person or any person to sit at a desk doing that, because we have a formula that involves E that will calculate it for us on its own. I call it the PERT equation. A is equal to P times E raised to the RT power. Now, the P is still the principal. It is still the amount that you start with. The R is still that annual rate. And remember, it's got to be written as a decimal. The T is still time in years. And the A is still the amount at the end. The A is still the amount in the account after T years. All right, so let's see this equation in action. Yeah,
So if it said like after 6 months, we have to do
a half of a year. 6 months would have to be a half of a year for T. Fantastic. Yep. 3 months, we're going to use a quarter of a year for T. Yep. So you deposit $3,000 in an account that pays 3.5% annual interest compounded continuously. What is the balance after 3 years? All right, Tara, what are you thinking we can write for this equation?
A equals 3,000
To the R is going to be 3.5%, which we're going to write as 0.035. Beautiful. Times T, which is 3. All right, calculator game. It is a calculator game. Take 3,000 multiplied by E to the 0.035 times 3 power. So if your calculator doesn't know PEMDAS, you're going to do 0.035 times 3, take E to that power, and then multiply it by 3,000. All right. How much is in that account, Miss Heather?
8,572.
I want to bank at your bank. Really bad. Okay. Can I ask, did everybody get that? Okay, good. What did we get? Good. $3,332.13. Remember, if they owe me the money, they're rounding this down. If I owe them the money on a loan, they'd make me pay the 14 cents. Okay, keep in mind how banks round, not to our advantage, but to theirs. Any questions? Okay.